last lecture was finished with contingency tables and the variant of chi-square criterion that is called McNemar's test. McNemar's test is introduced for 4 field table, 2 by 2 table, but the rows or columns are not independent uh, as in usual chi-square test. We can say that a patient or an object had some property before some intervention, and then he or she keeps this property. uh, we have 1 on the column, or it loses this property and properties disappear, so it was 1 and now it is 0. In other case, the second string, second row, gives us C patients that didn't have this property but got it, and D, this is the number of patients that didn't have this property and still do not have it. Actually, we compare B and C, so we compare only numbers of patients that change their property. A and B are not in the calculation. What is null hypothesis? The difference in the values of the studied feature before and after experiments is not significant. So the number of patients that loses this property is statistically the same as the number of patients that got this property. So we compare actually C and B. And the statistics has chi-square distribution, and the formula is like this. We subtract C from B or B from C. This is symmetrical formula because it's squared, and divide by sum B and C. If one of the at least one of cells A, B, C or D has less than n observations, then we should apply Edwards amendment, Edwards correction. Sorry, the Edwards correction is subtraction of 1 from difference between B and C. So this makes the result less, and we should have a bigger difference between B and C than usual when we have enough patients, more than 10 in each cell, because we subtract some absolute value from each addend. Sorry, this is only one addend, we subtract 1. Then, as usual, we should compare experimental chi-square result with critical found in chi-square critical values table when we have degrees of freedom as 1. This works only in case when B plus C more than 25. If it is less than or equal than 25, then we can calculate probabilities or p-value manually. How to do that? Let's B plus C is the number of all patients that change the feature from 0 to 1 or from 1 to 0. We will calculate the probability with relative with binomial distribution when probability of single event is 0.5. 1/2. So how to do that? We should summarize all events that has 95 in case of 0.05 significance value or 95 uh, confidence probability, uh, um, the least ones and the great and the greatest one. How to do this? So we select B or C, it doesn't matter which one, and we summarize all uh, values of combinations from M B plus C with 1, 2, 3 and other to B. So all values of E that less than B. And this is numerator and denominator is all probable variance of distribution between B and C in M. So this is usual binomial distribution that we had that we studied in the previous part of our course. And if this sum is less than alpha half of alpha, so alpha is significance level, so 0.025 to this is the least bound, the lower bound, and the upper bound is 1 minus 0.025. Then null hypothesis is accepted if it is independent. So if this probability is a small value, less than 0.05, or big value, so greater than 99, 97 and 75%, then null hypothesis can be rejected, and we say that changes of feature from 0 to 1 or from 1 to 0, it depends on which one is greater, B or C, is statistically significant. Let us consider the example. Students were tested before and after the training to improve the knowledge of the material. Experimental data represent the result of taking the test. Let the columns will denote the new test, second testing, and rows denotes the first testing before the training. 50 students passed before and after the training, so they had and still have good knowledge. These 19 students were confused with new knowledge, so preliminary testing they passed, but they failed test after the new material learning. So 31 students successfully improved their knowledge, and they, as we see, didn't pass the first testing but passed the second testing. And 20 students were sleeping during the classes, and they didn't improve their knowledge, they failed both times, before and after. We should apply McNemer test to differ students that how to say, that decrease their success on this subject, and with students that increase. So we have almost twice uh, more successful students than unsuccessful, but 31 and 19 is not so big numbers, so we don't know whether this difference 12 students is significant or not. So let's formulate null hypothesis. The difference in values of the studied indicator 19 and 31 before and after the experiment is not significant, so training was useless. As usual, null hypothesis tells us that something didn't have any effect. Let's calculate experimental value. This value is b minus c squared, so 12 squared over b plus c. The value of experimental chi square is 2.99 or 88, sorry. So if we look at the table of critical values, then we see that critical values of chi square is 3.84 for level of significance of 0.05 and degrees of freedom as 1. And so we didn't have enough difference to conclude that that classes was good, so our 2.88 is less than critical 3.84, and null hypothesis we conclude that is accepted. So the conclusion that difference in values of studied indicator before and after the experiment is not significant on the significance level of 0.05. The next criterion we will study is Fisher's criterion, or so-called F-test. This criterion is parametric. Two samples should be normally distributed, and we should calculate whether variances of those samples are the same. We shouldn't understand this equality as arithmetical strict equality. We should understand it as we do not have statistically significant difference between two variances. We can denote it as Vx or sigma squared of x. The experimental value of criterion is calculated like that, sigma 1 squared over sigma 2 squared, but sigma 1 should be bigger than sigma 2. We can change the sample with the bigger variance. So experimental value is always greater than 1, but the rejecting or accepting null hypothesis depends on how much it is greater than 1. We have two degrees of freedom for the first sample as number of numbers of patients in the sample -1, and the same formula for degrees of freedom in the second sample. Then we're comparing calculated experimental value as a ratio of squared sigmas with the tabular critical value as just like we did for other criterion, skewness, asymmetry, or kurtosis, excess, or Faucher squared, or Faucher squared for continuity table, or McNemer test. So just look at the table and find critical value and compare experimental with critical. Let us look more carefully to the critical table for F criterion. It's a little bit unusual for us because we don't have a significance level as head of columns. Now all table is for significance level of 0.05 or another table for significance level 0.01 and so on, and the third table for significance level of 0.001. What is in the table? Columns are the heading of column is degrees of freedom for the sample with bigger variance, and rows are denoted. The first column is the number of degrees of freedom for the second sample that has less variance. In our example, I remind we don't have example, I'm sorry. So in the intersection of degrees of freedom for our case, we should find some critical value and compare it with experimental. If experimental is greater, then we can conclude that null hypothesis is rejected. But if the difference, the ratio between variances, it's not so big to be greater than critical value, then we conclude that null hypothesis is accepted. This is written here. So now let's analyze an example. Let us study the effect of dietary supplements on the body weight of some laboratory animals. The experiment was conducted on two groups of animals. The intervention group, let me call it not experimental but intervention group, and control group. In the control group, sorry, in intervention group, the animals got dietary supplements to their food during the experience of weight. We got the following numbers in grams. Intervention group, this from half of kilo to 700, and control group is from 400 grams to a maximum 621. So we say that intervention group has bigger weight, but is this difference statistically significant or not is a question, because we have only 6 animals in the intervention group and only 7 animals in control groups. We know that the statistics works like this. The more objects we analyze, the easier we can find some effect. So those groups are maybe too small. Formulate zero hypothesis. Variances are the same in X intervention group and Y control group. The variance, the squared standard deviation of the first group is 4097. For the animals that feeded usually is 5 1143. So if we divide, we got the ratio. The ratio is 1.25. Then our degrees of freedom is 6 for the first sample for intervention group, and 5 for control group. Let us go back to the table. The bigger variance has intervention group, so it will be found by column. The number of degrees of freedom is 6, so let me check again. It's vice versa. I'm sorry, the first group is control group and the second group is intervention group, because the variance of the control group with 6 members is 5, sorry, is 4027. So we should move, I missed these things, sorry. So we should move from x and y to 1 and 2. The first group will be the group with bigger variance. The bigger variance is here for y, and y will be the first group with the control group with 6 degrees with degrees of freedom as 6 with 7 numbers. It's less in its mean value, but it's bigger by the variance. And the second group will be our intervention group with bigger weights, and its variance is 4000. So the first group has control group has degrees of freedom of 6, and intervention group has degrees of freedom of 5, and we take 6th column and 5th row, and our critical value is 4.95. We compare our experimental value of 1.25 with 4.95, and the experimental value is not so big to be greater than critical. So the difference between variances is just 1.25 less than critical, 4 times or almost 4 times less than critical f-test value, and we accept null hypothesis. So this supplementary dietary supplement is not effective. I'm sorry, the weights, we don't compare mean values. We don't conclude this that I wanted so that our dietary supplement is not effective. We conclude only that variances are not are equal, and do not differ from each other. And later, when we can compare mean values by students' criterion, then we can check the variant of student's criterion with equal variances. The next criterion we study is so-called student's criterion, or more frequently it's called t-test. This is parametric criterion, and it's very widely used. Even Excel implemented this criterion. The function name is t-test. It has several parameters. As other criterions, it should be two-tailed or one-tailed. It depends on whether we are sure that one sample is greater. If we are sure that one sample is greater than another, for example, it analyzes a set and another sample is a subset, and we just looking at difference between those numbers. If a set is obviously bigger than subset, but is it significantly bigger or not is a question. Only in this case we use one-tailed criterion. If samples are actually independent and we are not sure that one is obligatory bigger than another because of some unstatistical considerations, then we should take two-tailed test. And another parameters is about variances. The one formula for the equal variances, and another formula is for different variances, and how to check equality of variances by f-test we just studied. We will look at three variants of student's criterion. The first one is compare one sample with some number. For example, if we measure temperature in English medium group and compare the mean value with 36 and 6, then we should apply just the student's test for fixed value. Another one is a student test for two samples. We compare mean values between them and check whether this difference between mean values is significant. And the third variant we will consider at the end of our lectures is significance of correlation coefficient. And we will go to this variant at the end of course. So the variant number one, comparing the sample mean with fixed value. I remind that formulating zero hypothesis, we say that we compare not just mean value, but we compare mathematical expectation of overall population with this mean value. This is the criterion idea for all criterion. We take sample to estimate the statistics for all population. So formulating zero hypothesis, we should say about population. So the mathematical expectation of a sample is statistically equal to some fixed value mu. How to calculate the experimental value? We should subtract from mean value in our sample our fixed value and divide by standard error. Standard error is, as usual, we subtract from each value mean value, square it and summarize all those values, and divide by number of elements in a sample times number of elements minus 1. This number of elements minus 1 is degrees of freedom that we take into account while looking at a table of critical values. Uh, so for given alpha, the significance level for our small samples in practice it will be always 0.05. We compare our experimental value with critical one, and if this difference over uh, uh, standard error is not too big, then we accept our hypothesis that difference between expectation and fixed value is not significant, and if we have a big difference and small error, for example, then we conclude that our hypothesis can be rejected and our sample is something unusual. Its mean value is statistically different from fixed value. Let's look at some example. Let us have some random variable x is measured, and we have the following results: 15, 18, 13, and 14. Applying students' criterion, we should check whether the obtained mean value differs significantly from 0. Those numbers are quite bigger than 0, so it may look strange to check whether them difference from 0. But as I said previously, they maybe missed that this is usual task to compare some usual problem to compare some set of numbers to 0. It can be applied for differences. Later we will study so-called paired or criterions or criterions for dependent samples, when those numbers can represent the differences between uh, value of some parameter before treatment and after treatment. So for the first patient it's changed by 15, for the second it's changed by 18, for the third and for the fourth you see the numbers, and the effectiveness of treatment is calculated by those numbers, whether some parameter is changed to the big or not value, and are all those changes are positive, so plus 15, plus 18, plus 13, and plus 14, or for some patient it is decreased, and for some patient it might increase with minus. So those considerations are quite usual and quite frequent. So comparing the sample mean to 0 is quite a frequent task. So, but for these 4 patients, even there are only 4 numbers, probably we will see the difference from 0. Let's check. The mean value is 15, and then calculating standard error, we should subtract 15 from all of the numbers from 15, 18, 13, and 14, square it, and divide by number of numbers. So 4 times the number of numbers minus 1, 4 times 3. We obtain 1.08, sorry, and we should compare this value. Sorry, this is just the error, so it's in denominator. Then we should divide this value. Uh, this is missed. We should, following the example, we should divide 15 difference between our mean and 0 uh, over standard error just calculated. It is uh, 0.8. So if we divide this by this, we will get something about 13 or 14, and the number of degrees of freedom is 3 for numbers minus 1, and for significance level of 0.05 the critical value is just 3, but we have about 13. So we can even reject null hypothesis with significance level of 0.01 because 5.84 is still twice less than critical than experimental value of 13 and something. Thus we conclude that mean value and the expectation of our sample is different from 0 on significance level 0.01. The second variant of students' t-test is the comparison of two samples. Let it be sample 1 x and sample 2 y. And n1 is the sample size of the first sample, and n2 is the sample size of the second sample. The student's t-test null hypothesis states that mathematical expectations of x and y are the same, or the difference between the expectations is 0, or two samples belong to the same general population, all three statements of null hypothesis are equal. You can use any of them. How to calculate experimental value for students' t-test? The denominator is the difference between mean values x and y, and denominator is a variant of standard mean error, but not for one, not for two samples this time. If you remember the standard mean error for one sample, then you can remember denominator is this sum each x minus mean x squared, and in denominator is n times n minus 1. If you look carefully to this standard error, you will find lots of analogies. The first one is we have the same denominator as in standard mean for one sample, but the first one for the first sample and for the second sample, and just the same formula. In place of n minus 1, the number of degrees of freedom for one sample, we have degrees of freedom for the first sample n1 minus 1, and degrees of freedom for the second sample n2 minus 1. If we add, then it will be n1 plus n2 minus 2. And in place of n in denominator, we have n1 and n2, and this is sum of inverse values of n1 and n2. So the formula looks more complicated, but contains the same ideas, the same sized numbers. This standard mean error variant is used when variances of x and y are the same. We can check it using Fisher's f-test. Another variant of standard mean error for samples with different variances is here. We summarize variance, so standard deviation, sorry, not variances, but squared mean errors for the first sample and squared mean error for the second sample. We just summarize them and take square root from its sum of squares. Calculating standard error, then subtracting one mean from another over calculated standard mean error, we will get the experimental value of t-test for two samples. And as usual, if we have experimental value, if we have difference is big, high difference and small denominator, small variance in the first and in the sample and in the second sample, then we have big experimental value that can be greater than critical one, and in this case we can reject zero hypothesis and say that our samples are different. They are taken from different populations, for example healthy and sick patients. And if the difference is not very high, then and we didn't have the value of experimental t-test greater than critical t-test, then we conclude that we didn't find any difference between samples, and null hypothesis of same expectations is accepted. Let us look at some small example. Again, we have intervention group that got some drug, and the control group then got placebo, and we have measured some parameter. This parameter for intervention group is here. It's has a minimum of 120 and maximum 180, and here minimum we have 160 and maximum 220. Maybe this is critical systolic pressure, for example, and our drug decreases the systolic arterial pressure. Is it effective? Mainly we see that those numbers are less than those numbers. The x numbers is less than y numbers, but is this difference statistically significant or not? We are not sure, because we have very small samples, and this study can be just preliminary study. So small number of patients, but in order to show you all calculations, we cannot have big samples. So our null hypothesis states that the expectation of our parameters in intervention group and in control group are the same. So as usual, null hypothesis tells us that nothing significant is done, nothing is effective, everything is equal. In our case, we say that drug is not affected by null hypothesis. Firstly, we should calculate mean value for both samples. For the first one, it's about 150. For the second one, it's 180. And we see the difference is quite big. But the question is what about standard error? If it is big, you remember it is in denominator of student of formula. If it is big, that it can cancel difference between mean values, and we have small number, so this yeah, and this value of error can be big enough. So let's check. We will use the first formula, assuming that variances are the same. So we subtract from each x the mean x, square it and summarize. The same is done for the second sample, and following this formula we calculate. After calculation, finally we get the error, standard error for two samples as 12. This is quite big number, and difference is minus 33 because let's imagine this is system version, it's decreased, so the difference is negative, and we divide it by 12 and get less than minus 3, minus 2.68. The number of degrees of freedom is n1 plus n2 minus 2, it's 11. So let's go to critical values table. For students criterion, it's already done, and the critical value is 2.20. Don't make a mistake, don't take this value as negative and compare negative with positive. We should compare experimental value by its absolute value, and its absolute value is greater than 2.20. So with significance level of 0.05, we conclude that zero hypothesis is rejected because critical value is less than our experimental value. So our drug, even in this preliminary study, is effective. This is a standard output of some medical statistical program. We can check our calculations. The mean values is that and that, and difference between them is 41. Well, we had the same mean values. Let's check. Approximately this and approximately that. Variances, we can conclude they are very close. If to apply f-test, then we have a little bit more than one, but for our case, you remember the critical value of f-test are more than 2 at least. So the variances are the same, and we applied the correct formula for standard error of two samples. The number of observations is 6 and 7, and degrees of freedom is 6 plus 7 minus 2 is 11. t-statistics that we roughly calculated, actually roughly rounding our values to 148 and 181 is close. We got minus 268 and statistical problem minus 269. We have different samples, independent samples, so we didn't know how preliminary a priori how this drug works, and actually mean of the of the intervention group might be greater or less than mean of control group, and thus we should take two-sided p-value and two-sided criterion. And critical value is 2.20, just like we found in our table of critical values. And nowadays actually the significance is checked by p-value that we don't consider in our lectures and our practice, because it's impractical to calculate this value on calculators, so in most cases it's impossible. So we use old style considerations when we compare experimental value of t-statistics by its absolute value with critical value of t-statistics. The next criterion we will study is a non-parametrical criterion. This means that samples might not be normally distributed. In this case, we cannot compare using students' criterion, t-test, cannot use asymmetry and excess, cannot use Fisher's f-test criterion. But what to do? In order to deal with non-Gaussian samples, we should move from measured numbers to ranks. And next criterions will be ranking criterions that calculates ranks, and after that calculates those experimental value and compare to critical. Another difference between parametrical and non-parametrical criterions is comparing experimental and critical values. In this non-parametrical case, we reject null hypothesis if our experimental value less than critical. Unlike parametrical criterions, when we reject null hypothesis if experimental value greater than critical. The first criterion is Wilcoxon criterion, and this is the first criterion in our course deals with dependent or paired sample values. What does it mean? For example, we have a sample of patients, several patients, and some parameter was measured before and after treatment, and value for the patient A, value before and value after are dependent because they are for the same patient, and for all patients the values are paired before after. So let's consider xi is paired with yi for the same I patients. It's obvious that sample sizes should be the same, and we are interested in calculation of difference before after Was it positive difference or negative? Was the value decreased or increased? And our treatment is effective if all or almost all values were shifted to the same direction, to in positive direction or in negative direction. Uh, if the half of patients decreased their value and half of patients increased their value, then we should conclude that treatment is ineffective. And as usual, we should take some significance level where statistical significance will be tested. Uh, so let's consider what ranks are. How to move from measured numbers to ranks. So rank is a usual serial number when all numbers are ordered in ascending, for example, order. But if some measurement have equal results, then we should spread consecutive serial numbers between all or among all equal of equal values. Let me show this in the example. Let us have 10 measurements, and some of them are the same. So here for the third patient and for the ninth patient we have 2, and what else? 5. And for the first patient and for the fourth patient we have 5. So let's give ranks in ascending order. We have only one minimal value as 1, and the corresponding rank will be 1. We have 2 values of 2. This means that we should share 2 and 3 serial numbers between them, but they should be equal. Thus we should calculate mean value between 2 and 3 and give both 2 for the third patient and for the ninth patient the same rank. Rank is third half. Then next serial is 4, and we give 4 as a rank for 3. The next one is 4, we give rank of 5, sorry, and we have 2 5s. We should spread next 2 serial numbers, 6 and 7, and even we have 3 5s, so we should spread 3 ranks 6, 7 and 8 to patient number 1, patient number 4 and patient number 6. The mean value is 7, so all of them got 7, 7, 7 and 7. And the next serial is 9. 9 goes to 8, and 10 goes to 9. That's all. So we spread all serials as ranks to our 10 patients. So in Wilkerson criterion we use those ranks when we will rank differences. So the first sample x and the second sample y will use to calculate the one sample of differences, and we calculate those differences, subtract yi from xy, and then we apply ranking to absolute values of those differences. After giving ranks, we should remember which differences were negative and which differences were positive, and summarize ranks for positive values and negative values. Uh, then we should calculate minimum of this sum, and this will be the experimental value of our Wilcoxon criterion. Unlike parametric criterion, in this Wilcoxon non-parametrical or rank criterion, we reject null hypothesis if our experimental value less than critical, strictly less, and we accept null hypothesis if experimental value greater or equal than critical. Let's consider the example, and then I'll explain why this is unlike parametrical criterion. Let us have a control group. So let us have values of our sample before treatment and after treatment. Like this. For the first patient, the value of 32 goes to 21, so it decreased, and for the second one it's also decreased, for the third it's decreased. For the fourth patient, the value is slightly increased. For the fifth patient, our property is not changed, our feature is not changed, and for the sixth patient it's increased, and for other three patients the value decreased. So was the treatment effective? For the first two patients, probably yes. For the last three, also yes, but not with this effectiveness. And for patient number 4, 5, and 6, it is the treatment was not effective, even maybe some got negative effect. But these differences are small if they have the smallest ranks, and this gives us idea to finish this calculation the, and shifts positive shift negative from B to plus negative shifts maybe significantly greater than positive shifts with those two students. So first thing we should do is exclude from our calculation all patients that treatment didn't have any effect. So we exclude the fifth patient. Then we should summarize, then we should give ranks to our differences. The minimum is -1 by absolute value. It's 1, and it has the first rank as 1, and then we have negative how to say decreased value by 2 and increased value by 2, the opposite signs but the same rank values. So we should spread 2 and 3 between them, and we give 2.5 to both these values. After that we don't have any repeated values, so 4, 5, 6, 7, 8 goes to consecutive ascending ordered values 5, 6, 7, 11 and 12. So the last rank is 8, but we have 9 patients. This is because one of them is excluded. Null hypothesis, so differences between positive and negative shifts, positive and negative shifts, so increasing and decreasing value are significant. N number of patients is not initially 9 but it's 8 because one was excluded. Then negative R minus negative values for differences, there are only 2, and we summarize the ranks is 3.5. So we summarize this rank with this rank, so 3.5. And positive sum of ranks is 32.5, and minimum of those two values is 3.5. So according to the table for n equals to 8 and alpha 0.05, we find the critical is 4. Let's open the table for critical values, and our 8 patients gives us maximum critical value as 4, but we don't reach this maximum. We have only 3.5, very close. So our experimental value less than critical, and critical and zero hypothesis is rejected. So despite these two patients, we have to conclude that our treatment is effective. Why? I want to give you an idea why, unlike parametrical criterion, we reject null hypothesis when our experimental value is less than critical. What is experimental value? Experimental value is minimal sum of ranks for our shifts. Let's look at this example. This minimum here is 1 plus 2.5. If we had no such patients with negative values, then minimum would be just 0. So if our treatment is effective, all patients have positive shifts, then experimental value is just 0. And the more differences between patients, some of them decreased the value, some of them increased the value, the more differences, the greater experimental value is. So if this minimum is big, this means that negative and positive shifts are the same, and this means ineffectiveness. And the less experimental value, the less differences between result of treatments in the means of increasing or decreasing. But in parametrical criterion, if you remember, then experimental value is accumulation of differences. So the idea of criterion statistics are different. The next criterion is also rank criterion. It's analogous students criterion. We compare not paired, not dependent, but independent samples, but those samples could be not normally distributed. First, let's order our samples. Uh, let's denote n1 is a sample, is a number of objects in the sample, in the smallest sample, and n2 is number of objects in biggest sample. It's just notation. It will be useful when we look at critical for criterion tables. So let's think always that sample size of first sample less than sample size of the second sample. Null hypothesis is like in students criterion that differences between samples is insignificant. So we cannot say mathematical estimations, so we will not calculate mathematical estimations themselves. So we will go to ranks. Thus we will just say that differences, there are no differences between samples. And again, since we have two rank values, we have not just a formula to calculate experimental values, but even an algorithm to calculate it. We should, on the first step of the algorithm, we should mix all values from both samples and give ranks for all n1 plus n2 values for all values. After that, we should summarize again ranks for the first sample. This will be R1, and for the second sample this will be R2. And in order to take into account sample sizes that are different, we subtract some expression depends on sample size. This for the first sample n1 times n1 plus 1 over 2, and for the second sample the same formula in the sample size of the second sample. After that we take a minimum again from those two values, and with those minimums we will go for finding critical value or p-value. In this case we have two types of table for the criterion. If the biggest sample size n2 less or equal than 8, then we will have the special case of criterion tables. This special case is given for each n2 starting from 3, 4, 5, 6, 7 and 8. And the rows of this table is denoted by n1 and is denoted by experimental value, this minimum, and columns is denoted by n1, the sample size of the first sample. And in the intersection of n1 column and ux row, we find the so-called p-value. Uh, this p-value is actually probability of looking at found rank minimum of found these experimental statistics, and even worse when null hypothesis is true, when assumed that null hypothesis is true. It's conditional probability. And if this probability is less than a significance level, in our cases it will be 0.05, then we take zero hypothesis as not correct. So if probabilities of having these critical values when h0 is true, gives us idea that h0 is probably wrong. So we reject this hypothesis if p-value is less than alpha, and if p-value is greater than alpha, then we accept null hypothesis. If M2, the biggest sample size, is greater than 8, then we will use another table when in the intersection of row and column we have critical values and critical values for monoidtic criterion, and we compare our experimental value with critical. And in the same way as in Wilcoxon criterion, if our experimental value is less than critical, strictly less, then we can reject null hypothesis. And if experimental value is greater than critical, then we accept null hypothesis. Again, why it is unlike parametrical criterion. Let's have a look again to the critical values. This is the minimum of ranks of our samples. Imagine that our sample, the first sample, has smallest numbers like 1, 2, 3, 4, 5, 6, those ranks, and the second sample has all ranks that greater than in the first, 7, 8, 9, and so on. So this minimum is smaller than when our ranks are mixed in our samples. For example, first sample has ranks 1, 2, then 5, 6, 7, then 11, and the second sample have 3, 4, then 8, 9, and 10. So they are mixed. Then it's obvious that minimum will be greater in this picture in the first one, when the samples are ordered in that way that first the first sample and after that the second sample. So every mixture of those samples gives us increase in minimum, increase in experimental value. So the less experimental value, the bigger the difference between samples. That's why we reject null hypothesis with smallest experimental value and accept with biggest. Let's look to the example. Using Whitney criterion, check whether differences between the samples are significant for the significance level 0.05. This is very small study. The first sample has only 4 numbers, the second sample has 5 numbers, and we see that we obviously have a mixture because 7 and 8 goes after 3 and before 8, and 5 also is here. So the samples are intersected, but intersected only between smallest numbers of the second sample. If we no and 1, 9 goes here. So for this small samples, it's almost obvious that those samples will not have, I guess, will not have significant difference. But we see that the second sample will have generally bigger number than in the first one. So let's give ranks. The first rank to the smallest number, 1, the second rank to the next number. I remind we mix all values, so we give ranks for both samples same time. So 1, 2, 3 goes to 5, 5 to 8, 4 to 7, I missed. Then 9 will have rank 6, and 10, 12 and 13. The next rank 7, 8 and 9. The sum of ranks in the first sample is 14, in the second sample is 31, but second sample has one more member comparing to the first one, so we should subtract some value depending on sample size. So U1 is 4 finally, and U2 is 16. The minimal value is 4. And we should, since N2 is 5, we should go to a table for N2 equals to 5. Let's go there. Columns are numbered by sample size of the first sample, and the sample size of the first sample is 4, as I remember, and our experimental value is also 4, so our p-value for our case is 0.095, and this means that it's greater than 0.05, and we should conclude that our difference is not statistically significant, so we accept zero hypothesis. The second example, effect of different drugs on two groups of animals was studied, and the following results was achieved. We see that generally the size of the first group is not size but values in the first sample are less than in the second one, because the first sample doesn't has a big number like that, and we should calculate using Mann-Whitney criterion with significance level of alpha 0.05 again. Null hypothesis, as always, says that nothing happens, no difference, no effect. So in our case, difference between effects of some drug are the same in the first and in the second group. As usually, we give ranks. First, 1 goes to the 1, and we have two tools, and 2 and 3 goes here, 2.5, and for 3 we have 1, 2, 3 numbers, and we should spread 4, 5 and 6 ranks or serial numbers between those three values, and the average is 5, and 5, 5 and 5 goes 1 to the first sample and 2 to the second sample. After that we have 3 fours, and 7, 8 and 9 ranks goes there equally, so every element gets 8. And after that we have 10 and 2 fives. We have 10.5 ranks, so 10 and 11. And after that all numbers are unique, and we go with uh, sequentially next ranks: 12, 13, 14 and 15. Then we calculate sum of these. It's 29 and 5. Sum of these is 8.5, and then this is n1 plus into 15. Why do we need this? We don't need this. So, and u1 will be 8.5, u2 will be 45.5, so the minimum is 8.5. We'll look at another table because our biggest sample has more than 8 members, so we don't search for p-value, we search for critical value here, and 2 is, let me remember, and 2 is 9, and 1 is 6, and 2 is 9, and 1 is 6, so critical value is 10. What is our critical value, or experimental value? Experimental value is 8.5, and it's less than 9, so we can conclude that our drug was effective, and we reject now the hypothesis.